Good morning. Now, this is class 7 of our module Digital Electronics. Now, today we will learn about De Morgan's theorem. Okay, now this De Morgan's theorem, there are two statements for this De Morgan's theorem, and it is one of the most important session of this module. Okay, so this De Morgan's theorem, its statement, the mathematical expression, its proof, everything you have to study very well. Okay, now first theorem. This theorem was proposed by a mathematician called De Morgan, and that's why the name given as De Morgan. And this De Morgan statements, it will be very helpful for you to solve some Boolean expressions, which we will see today. So the first theorem, that is De Morgan's theorem 1, states that complement or inverting of the sum of two variable is equal to the product of complements of the variable. C, a plus b the whole bar equal to a bar dot b bar. That's the statement. That is complement of the sum of two variables, that is a and b, is equal to the product of their complements. Now, how will you represent this a plus b a complement? That is, you have can represent it using a NOR gate. How? You are giving a and b. So what will be the output of a NOR gate? Output of an OR gate will be a plus b, but output of NOR gate will be a plus b complement. So that is a plus b complement, and this is equivalent to a bar dot b bar. That is, here you are see a dot is there. So that will be given in this AND gate as a bar, and this will be actually b bar. So the output of the AND gate will be a bar dot b bar, because here there is a bubble. Okay, so here this a, when it comes here it will become a bar, when it comes here this will become b bar. So output will be a bar dot b bar. That is, a NOR gate is equivalent to a bubbled AND gate. This is another assumption that we can say. The theorem states that NOR gate and bubbled AND gate are equivalent. Both of them are same. This is the NOR gate and this is the bubbled AND gate. Okay. Now we are verifying this theorem by putting some values for a and b. First you are putting the values of a and b as 0. Then a as 0, b as 1. And finally a as 1, b as 0, a as 1, and both a and b equal to 1. Now you are verifying whether LHS is equal to RHS. Left hand side is equal to right hand side, that is a plus b the whole bar, that is LHS equal to a bar dot b bar. Let us see one example. You are putting both a and b 0. So what will be the LHS? 0 plus 0 is actually 0, but 0 bar will be 1. Okay, then that is, so LHS is 1. Now what about this RHS? A is 0, so a bar will be 1. Then b is 0, so b bar will be 1. So 1 into 1 will be 1. So LHS equal to RHS. So that particular statement, that is a plus b the whole bar equal to a bar dot b bar, is proved. So similarly you can prove this for various values by substituting various values for a and b. So here the statement you have to study, the expression, that is a plus b the whole bar equal to a bar dot b bar. Then an OR gate is equivalent to a bubbled AND gate, like that, and then the verification. Okay, now theorem 2 of De Morgan's theorem states that a bar dot b bar equal to a bar plus b bar, that is, the product of the complement of two variables a and b is equal to the sum of their complements. So how will you represent this a bar dot b bar? Using an AND gate. This is the input. You are giving an input a, this is output b. Since it is an AND gate, what will be the output? A dot b. Okay, now since there is a bubble, you will call it as a NAND gate, so the output will be a complement also. So a bar dot b bar, this is equivalent to a bar plus b bar. Just here there is a bubble, so what will happen? This a, when it reaches here, that will be a bar. When this b, when it reaches here, this will be your complemented b bar. Now since this is an OR gate, this a bar and b bar will be added, so output will be a bar plus b bar. So we can say that a NAND gate is equivalent to a bubbled OR gate. Okay, then again similarly the verification, that is a bar dot b bar, that is LHS equal to a bar plus b bar. So what is the LHS? A bar dot b bar equal to a bar plus b bar. First you are putting a and b as 0. So 0 bar will be 1. Again 0 bar will be 1. So 1 dot 1 will be 1. So this is proved. LHS is proved. Again what about RHS? A is 0. So 0 bar will be 1 plus again b is 0. 0 bar will be 1. 1 plus 1 is again 1. So LHS equal to RHS. So this is proved. Okay. So this is how it is said. So compare these two theorems and study very well. So theorem 1, a plus b the whole bar equal to a bar dot b bar, and theorem 2, a dot b the whole bar equal to a bar plus b bar. Okay. Now we are trying to solve some sample problems, Boolean expressions. So when you are given a Boolean expression to simplify, first you have to solve the thing that is given in parenthesis. Then you have to evaluate anything that involves not operation. Then comes AND operation, and finally you have to go for OR operation. So let us solve this one. Here question is y equal to a dot a bar plus b. So you are expanding it. So what will be it? A dot a bar plus a dot b. What is a dot a bar? It is 0. This we have studied some theorems, like I think some 11 or 12 theorems you have studied. A plus 0 is like that, a plus a bar is 0, like that. So refer those theorems. So a plus a dot a bar is 0. So 0 plus ab is again a dot b. Okay. So study this theorems well, because that will help you in simplifying such Boolean expressions. Now another one, this one. So here the common factors are a b bar. Here also there is an a b bar. Here also there is an a b bar. Okay. No, here I think c is common. So from here you can say take c outside, like this. A b bar is kept as such. Now again from here a bar c is common. So a bar and c is taken outside. The rest is written here. This is as such. Now what is b plus b bar? It is 1. So this will reduce to a bar c plus a b bar. Okay. Now another one. See this, you are actually expanding. AB plus AB plus AC plus BB plus BC. Okay. Now here in this step by step you have to simplify. Here B dot B. What is it? It is B itself. The rest is kept as such. Then this is all the same. Here B is common. So you take it outside. Okay. Then from here AB plus AB. This is written as such. Then AC is written as such. 1 plus C is actually 1. So this will reduce to B. Then what is A plus A? It is A. So what is AB plus AB? It is AB. Then AC is kept as such. B is also kept as such. Now here which is common? B is common. That is here this one B is common. So B within brackets a plus 1, then AC is kept as such. Now a plus 1 is 1 itself, so this will be reduced to B plus AC. Now this one, this is very simple. See how they are reducing. This is a question itself. Here this much is correct. Here see this PQRST plus PQRSTU. So PQRST is common, so that is taken outside. 1 plus U is here. Now what is 1 plus U? It is 1. Okay. So this will reduce to 1. So you are left only with this. Now among this in these two, PQRS is common. So PQRS is taken outside. 1 plus T is kept as such. 1 plus T is again 1. So this will 1. So this will become this. Again from this PQR is common, right? So PQ plus PQR, 1 plus is taken. 1 plus is 1. So this will be PQ plus PQR. Again from there PQ is common. PQ within bracket 1 plus R. 1 plus R is again 1. So it will be PQ. So Z is equal to PQ. But in the question you are asked to find Z bar. So what is Z bar? Z bar will be PQ bar. What is PQ bar? P bar plus Q bar. How you got this? This is De Morgan's second theorem. Okay. Now, this one. Here also the question is given as such. X bar, Y bar is taken outside, and in within brackets you have X bar plus Y. And here what you do is you are expanding X bar plus Y into X plus Y. You are writing, that is X bar plus Y bar into x bar plus y. How this one comes? How this xy the whole bar becomes x bar plus y bar? De Morgan's theorem, because we know a bar dot b bar or ab the whole bar equal to a bar plus b bar. So what will be xy the whole bar? X bar plus y bar. So this is, as per this, becomes like this as per De Morgan's second theorem. Now this is kept as such. Now you are opening the brackets and expanding. Then finally x bar, that is a bar dot a bar is a bar itself. So x bar dot x bar is equal to x bar itself. Then all these things is kept as such. Then finally here x bar is common, it is taken outside, the rest is kept as such. Then again 1 plus y is 1 itself, so this will become x bar plus this is kept as such. Then finally here x bar is common, so x bar is taken outside, and within brackets you will have 1 plus y bar. Then this itself it is kept as such. 1 plus y bar is equal to 1. So it will be x bar plus y bar y. Okay. Now similarly you can solve all these problems, nothing much confusing. Here also b bar plus b bar, it is taken as 1. So this also are simple problems, you can go through all these things. And this is something lengthy, so I will explain. This is kept as such. This is a question. So here you are expanding it. A bar, this one, a bar dot b bar c plus a dot b bar c plus a dot b bar dot bd plus then this one a bar dot b bar dot c. Okay. Now this is kept as such. Here b bar dot b, it is actually 0. Okay, as per the theorem. Then d, then everything is kept as such. So this becomes 0. So you will be having only this one. Now you are expanding, you are opening the brackets and expanding. C bar dot c dot c is c itself. Then this is kept as such. And finally the common term is c, and you are taking it outside. B bar and c is common, so it's taken outside. Now a plus a bar is 1, so the answer will be b bar dot c. So this is how you solve Boolean expression. So in this session the most important one is the statement, the expression, the representation using gates of this De Morgan's first theorem and second theorem, and then its verification, and finally simplification of Boolean expression using the theorems that you have studied plus the De Morgan's theorem. Okay, so you can go through it, work out more problems like that is how to simplify Boolean expressions. Okay, that's it for now. Thank you.